Hello, everyone, and thank you for being here. I will represent our group head to introduce all our members here. So our leader is Fuk Sang, and I'm Yongjia Ken. And the rest of my group mates are Tan Jing Hong, Tiang Yu Hao, and Lo Zhongyi. So I'll be giving a brief overview of a statistical study we conducted to explore something that most students can relate to, whether or not the amount of time we spend studying each week has an impact on our academic performance. Okay, on to the next slide. So to investigate this, we use a database, the data set containing information about 50 students. For each student, we had details such as how many hours they studied in a week and their test scores. The main focus of the study was to see if there's a noticeable relationship between how much someone studies and how well they perform in their exams. Now, we all assume that more studying should lead to better results. But what if we wanted to know what was really the case? Is that actually backed up by data? And if so, how strong is that relationship? We use standard statistical methods to examine this, and my teammates will explain those parts in more detail later. But before we continue, I will be talking about the task distribution given in the group. So Fuk Sang and Liang Yehao did the calculation. Jing Hong graphed out the chart. Me, Yong Jia Ken finalized and compiled the project, and Law Zhongyi collected all the data.
My name is Lao Zhongyi. I'm going to show you how we generate stimulated data for data collection. This is our data. For this project, we generate stimulated data of 50 students by using Microsoft Excel to explore the relationship between study hours and performance score. First, we create a list of student names include Alice, Bob, and many others up to 50 in total. Next, we estimate the number of study hours per week for each student. We assume that on average, student might study around 42 hours weekly with a reasonable range from 0 to 84 hours. Using this Excel formula, we produce realistic study hours data following a normal distribution. Then we generate performance score as a proxy for test score. This is the formula we use for performance score. This formula works by first scaling each student's study hours to a score out of 100. Then it adds a random adjustment draw from a normal distribution with an average of 5 and standard deviation of 3.5. Skewed so that large boosts are rare but small changes are common. This helps stimulate real-life difference where most students perform close to expectation but a few do unexpectedly better or worse. Additionally, we include gender using this formula, assuming a slight male majority and randomly assign age between 18 and 23 using this formula. Overall, this stimulated data set provides a practical and controlled way to analyze patterns between study hours and performance score.
A very good morning to my lecturers. My name is Tan Jing Hong, student ID AIT 2409079. So now let's me quickly go over the descriptive statistic for study hours. For the first value we get for the mean is 41.84. How we get this? We calculate this by adding all the study hours and dividing it by 50 students, which is the total number of students in our dataset. The median, which is the median value when we sorted it in ascending order from the dataset. And if the order is even number, we need to take the middle two value and dividing it by 2, and we get the value 41.4 for our median. The mode, which is the most frequent number appear in the dataset. For this, we get 51 hours from our dataset. And standard deviation measures how spread out the data is. To calculate the standard deviation, we need to first find the variance and averaging the squared difference from the mean. Then take the square root. After that, the calculated data we get is 14.21, and this is the standard deviation from our dataset. The range, we calculated it by using the maximum value minus by the minimum value. The maximum value is 76 hours, and the minimum value is 6 hours. So the range of study hours per week is 70 hours. And these statistics give us insights into the study habits and also variation in study hours. Next, let us look at the study hours data. And the first diagram is about box plot of study hours, and the second diagram is histogram of study hours. The box plot shows the median study hours is around 42 hours per week, with most students studying between 35 and also 49 hours. The interquartile range, which we also known as IQR, covers the middle 50% of the data, spans from 35 hours to 49 hours. And the outliers indicates a few students study much more than the rest. Next, the histogram shows that most students study 35 to 49 hours per week. The distribution tails off as study hours increase, with fewer students studying more than 60 hours. And these two visuals show the spread central tendencies and also IQR of study hours. Lastly, let's look at the scatter plot showing the relationship between study hours and also the performances score. The scatter plot indicates a strong positive correlation between the two variables. As the number of study hours increases, the performances scores tend to rise as well. And from the plot, we can know that the equation of line is y equals to 1.2117x plus 10.643. And the r squared value is 0.8931. And this high R squared value suggests that study hours explain almost 90% of the variation in performances score. And this highlights the significant impact of study hours on student performance. That's all from me. Thank you.
Thank you, Jing Hong, and good morning, lecturer. My name is Liang Yu Hao, and my student ID are AIT 2409073. So in the next part, I would like to talk about the correlation analysis. So in this part is more about the calculation. We will first perform a Pearson correlation to check the strength and direction of the relationship between hours study per week and test score. And these two formula at the bottom of the slide we are going to use. And we also include some data, which is the mean for the hour study per week, which is 41.84, and the mean for the test score, which is equal to 61.34. So in the next part, as you can see this paper represents our calculation, and we write it out one by one and calculate by the calculator. Like for the calculation step, for step one, like for student one, he used 19 hours to study per week. So we will use 19 to minus 41.84, which is the mean for the study hour per week. And we will times the test score for student one, which is 29.12 minus 61.3422, which is the mean for the test score. And we will repeat this process for student 2, student 3, student 4 until student 15. And then we will sum up together and we will get a result of 20,000.2112. And in step 2, to find out the covariance, we will use the result, which is 20,000.2112 to divide the total number of students minus 1, which is 49. And we will get 244.94308557, and then we'll use it to calculate the R, and at the end we will get 0.9466. And since the full Pearson correlation is equal to 0.9466 and it is near to positive 1, so we can conclude that it have a perfect positive correlation.
Thank you, Yuhao, for presenting the correlation analysis. My name is Fuksang, and I will now explain how our group performed the hypothesis test. We used a one-way ANOVA test to carry out the hypothesis testing. First, we define our hypothesis. The null hypothesis H null states the means of all three groups U1, U2, and U3 are equal. The alternative hypothesis HA states that at least one group mean is different from the others. Next, we divide the students into three range-based groups based on their weekly study hours, where the first group is less than 30 hours, second group is 30 to 50 hours, and the third is more than 50 hours. As shown in the photo beside, we arrange the test scores data according to each student's study hours per group. The first step in the ANOVA test is to calculate the mean test score for each group, which we label as Y mean. Then we use the mean test score we just calculated to continue the process. We calculated the sum of squares between groups SSB and the sum of squares within group SSW. After that, we determine the degree of freedom for both between group and within group variations. Next, we compute the mean squares by dividing the sum of squares by their respective degrees of freedom. Finally, we calculate the F statistic using the ratio of mean square between group to the mean square within group. Here is the formula for the steps we use. The first image shown here is used for finding the mean of each group and also includes the formula for calculating the sums of squares between groups and within groups. To find the sum of squares between groups, we use the summation of the group number of students in each group represented by Ni multiplied by the square of the difference between the group mean and the overall mean. For the sum of squares within groups, we use the summation of each student's test score minus the mean of their respective group. The square the result and then add them up across all groups. For the degree of freedom, we calculated two values. The degree of freedom between groups is k minus 1, where k is the number of groups, which in our case is 3. The degree of freedom within group is n minus k, where n represents the total number of students. After that, we calculate the mean squares. For the between group mean square, we divide the sum of squares between group by its degree of freedom. This value is also referred to as MSB, which stands for mean square between groups. For the within group mean square, we divide the sum of squares within groups by the corresponding degree of freedom, which we call MSW, or mean square within groups. Finally, to find the F statistic, we divide the mean square between groups by the mean square within groups. From our calculation, the F statistic value is 79.4430, shows here. Here we set the significance level at 0.05. From our calculation, the degrees of freedom between groups DFB is 2, and the degrees of freedom the degrees of freedom within groups DFW is 47. Using this value, we refer to the F distribution table to determine the F critical value, which is 3.23. According to the decision rule, for the F test, if we calculated F value is greater than the F critical value, we reject the null. We reject the null hypothesis. If the F value is less than or equal to the F critical, we fail to reject the null hypothesis. In our case, the calculated F statistic is 79.4430, which is clearly greater than 3.23, so we reject the null hypothesis. In ANOVA testing, we usually use the F statistic to make the decision, but we can also use the p-value approach. To do that, we use an online calculator to determine the p-value based on our F statistic and degree of the freedom. The p-value we obtain is 0.00000022, which is extremely small. Since this p-value is much smaller than our significance level of 0.05, we again reject the null hypothesis. That's all for my part. Now I will pass the presentation to Jiaken, who will conclude our findings and present the final results from our group.
So, after analyzing the data, here's what we found. There was a very strong positive relationship between study hours and test scores. In simple terms, students who studied more tended to perform better. This was backed by a correlation value of 0.9466, which is very close to a perfect positive correlation. Meaning that as study hours increase, test scores increase too. We also compared different groups of students based on how many hours they studied. For example, those who studied less than 30 hours, between 30 and 50, and more than 50. And the results show a significant difference in test performance between these groups. In fact, a statistical test called ANOVA gave us a very high F value and a very small P value, which told us that the differences we saw were not random. They were statistically meaningful. Of course, this was stimulated data, so it doesn't reflect every real-life factor. Things like study quality, sleep, motivation, and mental health all play a role in how well someone does. But based on this data alone, it's clear that more time spent studying is strongly linked to better academic outcomes. So to sum it up, yes, study time does matter, and according to our results, it can make a big difference. Thanks for watching, and I hope you have a great day.